In the previous lecture, we were discussing weak maximum principle for the solutions of the heat equation. We were in the just finishing part of that proof. So let me just recall again. Okay, so what is the weak maximum principle? So if u sub t minus Laplacian u is less than or equal to 0 in a domain in Rn plus 1, okay, so that domain we are taking, so omega is a bounded region in Rn and t is any positive number given, and we defined what is meant by parabolic boundary in this situation. And then the statement of the weak maximum principle is if ut minus Laplacian u is less than or equal to 0, then the maximum of u or omega t bar is same as maximum of u taken over the parabolic boundary. Okay, of course, this does not rule out that the maximum of u can occur somewhere in omega t bar other than the parabolic boundary, and the strong maximum principle rules out that in certain situations. Okay, so this proof of this statement follows by taking this auxiliary function v of xt, which is equal to u of xt plus epsilon mod x square, where epsilon is a small positive number, and we showed that the maximum of v cannot occur outside the parabolic boundary, and that in particular implies that maximum of v over omega t closer is same as maximum of v over the parabolic boundary. To assert the same thing for the function u, we have to just observe the following facts. So by the definition of v, we have this relation between u and v. So u is obviously less than or equal to v, and v in turn is less than or equal to u plus some constant times epsilon, where this constant is the maximum of this mod x square taken over omega bar. Okay, so there is no t here. Okay, just, so for weak maximum principle, this auxiliary function or test function is a very simple one, but for strong maximum principle, we need construction of some special test functions which are not trivial. Okay, so using this relation, now we take the maximum of u over the parabolic boundary, and parabolic boundary is subset of omega t bar, so maximum of u over the parabolic boundary is obviously less than or equal to maximum of u over omega t bar, and since u is less than or equal to v, so we have this maximum of u over closure of omega t is less than or equal to maximum of v over the closure of omega t, and just now we have shown that this maximum is same as maximum of v over the parabolic boundary, but then v is less than or equal to u plus c epsilon, so that is less than or equal to maximum of u over the parabolic boundary plus this constant c epsilon. Okay, just you pay attention to these three terms. That's just this one, this one, and the last. Okay, so if you write that thing, so we get maximum of u over the parabolic boundary is less than or equal to maximum of u over the closure of omega t, which is again less than or equal to maximum of u over the parabolic boundary plus some constant times epsilon. And now letting epsilon equal to 0, gives the result. So namely maximum of u over the closure of the whole domain is same as maximum over the parabolic pole. Okay, so and that completes the proof. Okay, so this, and that's what we wanted to prove. And for uh, weak minimum principle, so you have to just replace u by minus u, and for if equality occurs here, then you apply this result to both u and minus u. So then you have maximum, when you satisfy the heat equation, then maximum of mod u. Okay, so you can replace that by mod u over the whole boundary is same as maximum of mod u over the parabolic boundary. So as a closing remark, so this is not just special for the heat operator, so you can just extend this uh, weak maximum and minimum principles for a general parabolic operator, which is of this form: L is equal to uh, this del t, so that's partial differential operator with respect to t, and then you replace the Laplacian by a general elliptic operator. Okay, so aij are smooth for aij, and bi and c are smooth functions defined in some domain in Rn plus 1. The important thing, the assumptions on aij, so they are symmetric, and this is referred to as uniform ellipticity. It's nothing but the matrix, symmetric matrix with entities aij is uniformly positive definite. Okay, but in this context, it's also referred to as uniform ellipticity, and there is a sign condition on C. Okay, with these assumptions, again one can prove uh, weak maximum and minimum principle for solutions of LU equal to 0. Okay. So that's not difficult, and just it uses some simple property from linear algebra. Okay, so that we'll discuss in assignments. Okay, with this thing, now we move on to another qualitative property of the solution of the heat equation, and this is the mean value property. uh, and in this context, so we are taking average over a set, which is known as heat bond. So we'll define that thing. So for just fix an element in Rn and T in a real number, so it need not be one positive, okay, and R is positive. Okay, then this define this set EXTR. Okay, so this is a subset of Rn cross Rn R. So for this region, so since T plays the role of time, also referred to as space-time domain. Okay, it's bit looks complicated, but we'll just unfold what that is. Uh, so the CXTR consists of all elements ys, y is in Rn and s is a real number, where s is less than or equal to t, so t is given to us, And this is the fundamental solution of the heat operator. So this is. So this set is defined in terms of the heat kernel, the fundamental solution, and this is referred to as the heat bond. It is not exactly a ball. We'll see the geometry of that, but it looks like a ball. Okay. So this set EXTR. So for given X in Rn and T in R and R positive, okay, it's referred to as heat bond. So let's just examine. Okay, before examining what the set is, so let me just state the theorem. Okay, so okay, here it is. So let U satisfy the heat equation in a region Q in Rn cross R. Then for Xt in Q, Uxt is equal to this integral. Okay. And why it is called a mean value theorem or mean value property, and where are we taking the average? So we'll discuss all those things. Then you will understand why it is called mean value property. Okay. So this is true for any R positive such that this heat ball is contained in this given region Q. Okay. Okay. Before going into that, so let me just recall again. Okay. So this just as so for harmonic functions, so we saw, so this is Laplacian 0. Okay, this MV mean value property is equivalent to harmonicity. And for mean value here, so we used, so mean value means here either average over a sphere or a ball. Okay, so this we studied in detail on a ball. Okay, so obviously here we cannot take a surface or a ball in Rn plus 1 because there is no ellipticity here. So this, there is lack of one derivative here. So this Laplacian. So this only first order. Okay, so we cannot expect that. So in essence, this mean value property for the solution of heat equation may not look as elegant as in the case of harmonic functions, and also this equivalence. So for harmonic functions, we saw the mean value property is equivalent to harmonicity. That is also not clear in the present case, in the sense that suppose U satisfies this mean value property for all EXTR in Q, does this imply? Big question mark. ut equal to Laplacian. So that is not clear. Okay, so there lots of things to be uh, still analyzed, found out, and whether this kind of mean value is the best possible thing, or are there other ways of finding the mean value. Okay, so in this case, let me quickly uh, say this thing. Okay, so there is we are not just integrating the function, but there is a weight. Okay, we are multiplying by some function, so these are generally referred to as weights. Okay, the property of this weight is, okay, so if you remove this uys, okay, so this integral over, so I am writing here double integral just to indicate that this is n plus 1 dimensional integral. Okay, so y is in, this is one integral is in n dimensions and another one is one dimension. So if you integrate this weight function, namely mod y square by s square over this heat ball, and then you divide by 4 to the Rn, this is equal to 1. Okay, so this is a good exercise in computation of some integrals. Okay, so that means we are indeed taking average of uy, the function u, over this heat ball. Or the right hand side indicates, so average of u over e with some weight. So this is indeed average. So and the mean value property say that this uxt is equal to this. Uh, Proof is simple but lengthy and involves many computations. So first let's understand what is this EXTR. Okay, the heat ball. Okay, so let's analyze that. So let ys belongs to EXTR, then by definition s is less than or equal to t, and this kxtys bigger than or equal to Rn, and that you express here. Okay, so I am just expanding what is k, this fundamental solution heat operator. And since this is exponential with a negative exponent, so this is always less than or equal to 1. So that further implies that, so if you just consider this factor and that factor, so this is less than or equal to 1. So you find that 4 pi t minus s is less than or equal to r square, or s is bigger than or equal to r square minus r square t minus r square by 4 pi. Okay, so the s variable for any point in this heat ball is a bounded interval. So that's the first observation. Just from the definition, it's not even clear whether the heat ball is bounded or not. So at least the s variable is easily seen to be bounded and it lies in this interval. Okay. Next you rewrite this inequality. okay, as exponential x minus y square by 4t minus less than or equal to r to the n blah blah blah, and then you take the logarithm on both sides and you get x minus y square is less than or equal to this quantity, and this quantity for s lying in this interval is always non-negative. Of course it depends on s, okay. So what it gives us, so for each level s, so this is just defines a ball, yeah, here this represents a ball in Rn, center at x, that's the given point in Rn, and radius rho, okay. And as s goes to t minus, s is always less than or equal to t, so this radius becomes 0, and same thing as s goes to the other limit t minus r square by 4 pi. So at both values of s, obviously y has to be equal to x because this is non-negative thing, so stress that. So when this is right hand side is 0, y must be x, okay. It's not a good figure, but okay, I have drawn here, okay. So for each s you get a sphere in Rn, and then we get this xt at the top of this heat ball, and it's in the center. So here also this is s coordinate is x, and this one is r square by. So exactly not a ball, but a very nice, so it's union of spheres uh, for these values of s, okay. So heat ball is nothing but you get several balls and then you take the union. So it's a nice smooth domain. Yes. And smooth bond. In fact, boundary soon we'll see that it's given by a function, zero set of a function. Okay, so xt is not in the center, just like for the harmonic functions, but xt here, the point in question is in the top of this heat wall. Okay. So as I said, proof involves several computations. So we'll start with first reduction. So observe that the heat operator, heat kernel k satisfies this k of x comma t ys is equal to k 0 x minus y t minus s. So we can always do translations and assume that x is 0 in Rn and t equal to 0, a real number. And in that case, we write this E00R as simply E of R, that the 0 is fixed. And then the statement of the theorem, we need to prove that U00 is equal to 1 by 4 Rn Uys etc. over integrated over ER. So here R is any positive number such that ER is in the given domain Q. Okay. So let's re-examine what are the points in ER. Okay. So just again, so Ys. So now t equal to 0. So S belongs to this closed interval. and we have this sphere in Rn. So now centered at the origin and with this radius square. Okay. So the idea of proof is you consider this function chi of r. So it is same at the right hand side except for the factor 4, that's a constant. So just omit it for the time being. So the idea is to show that this integral, this function chi of r as a function of r is a constant. Okay, and then that will reduce, that will immediately deduce the result. Okay, and to show that this function chi of r is a constant, so we would like to take its derivative with respect to r, but that r occurs in the uh, integral, so that's in the domain. So then that is very complicated, so we'll try to push this r in the integrand so that we can easily integrate. Okay, so for that you change the variables, so y equal to r j and s equal to r square tau. Okay, with this change of variables, and this ys belongs to er if and only if xi tau belongs to e of 1. Okay, so that reduces to e of 1, and a simple uh, computation shows that the chi r, which is given by this, is equal to e of 1 u of r j r square tau mod j square by mod tau square d j d tau. Okay, so we'll be going back and forth with this change of variables couple of times, and now we can easily integrate this function chi with respect to r because r appears only in the integrand, so we can just uh, apply differentiation and the integral sign, and so we get this d chi by dr. Okay, so you carefully do it. There are many steps here, so but carefully do it. They are all simple. There is absolutely no problem. Once you do this thing, again you go back to the ys variables. So that's what I'm saying. So from ys variable we came to xi tau, and again from xi tau you go back to ys variables. Okay, and there are two terms here. Okay, so I am writing them separately. So this we are calling as a, and this as b. Okay, so now we consider the integral this beta and try to uh, analyze that term in detail. So this factor is okay. This factor du by ds, and that too can replace it by Laplacian u later. But what about this factor? Okay. And that factor somehow we want to connect it to this er and try to express in terms of er. Okay, and that's where this function is introduced, this ys. If you go back again, it's not a mystery, it is here. Okay, so it's psi comes from this relation. Okay, so it's coming from the boundary of er precisely. Okay, so define this psi of ys mod y square by 4s minus n by 2 log minus 4 by s plus n log r. It's precisely that one. Okay, just remember that. So I'm just dividing by that, and this replacing it by equality. Okay, and then you see that psi is 0 on this boundary of ER, which is given by equality sign. Okay, that's and now so that's we replace this mod y square by s in terms of this psi, and psi is related to the boundary of ER. So now you observe that del psi by del y I is 2y I by 4s. Okay, let's keep that for here. Okay, and now again you multiply by yi and sum over all I. Okay, so that's so this gives me 1/2, and that gives me mod y square by s. So in this b integral, so this is our b, I am going to replace this mod y square by s by this in terms of this del psi by del yi, and that's what I have done. Okay, so there is that there is already a 2 there in b, and now another 2 is coming from here, so that makes it 4. Okay, so this is sum over I. Okay, just remember that. Okay. And since now it is differentiation of psi with respect to yi variable, so integrate by parts. Integrate by parts. That is with respect to only y variables, because there is only derivative with respect to y. So there are two terms here. Okay, so when you uh, integrate by parts, so there is a negative sign here, and once you take the differentiation with respect to yi, and that produces n, because there are n terms, and there is another one, so you are taking differentiation of del u by del s with respect to yi, and that will produce this one. So we have two terms. Okay. And now in the second term, so here with respect to y variable, and now again integrate by parts. Now with respect to s variable. Okay, and s variable only here, so this will remain as it is. So I want to take this s derivative to this psi variable. So y does not depend on s, so y remains as it is, and now we get del psi by del s. Just keep observing the signs. Okay, and now again you simplify little bit, and now you substitute this del psi by del s. So psi is here again. This is the function. Now you take differentiation with respect to s variable, and that's what you get here. Okay, and now you simplify, so you get a nice expression. So this, the first term gives me this additional term, and second term is precisely a. Okay, again you go back and check here, so this is a. So with del u by del yi mod y square by s square, and that gives me a, and that is minus a. So therefore, so this all computation is for b, okay, and d chi by dr is a plus b, and now I have b is equal to something minus a, so that a plus b will be this expression, and that's what I'm writing. Okay, this is the expression. Okay, and so far we have not used that you satisfy the heat equation, so this is for the first time we are using. Okay, so this del u by del s is replaced by this. Okay, so del u by del s. Here we are using y, so let me write that. So all of this y. Okay, and again, since again Laplacian is there, so again integrate by parts with respect to integrate by parts. By the by, just notice here we have integrated by parts, but there are no, usually there are boundary terms. So let me just comment that there are no boundary terms as psi is equal to 0 on the boundary. And again let me stress that, so this boundary boundary is given by this. Okay, so boundary of ER is nothing but 0 set of this nice function. Okay, so boundary is smooth, so this integration by parts is justified, and there are no boundary terms as I is 0 on. So remember this, just use everywhere. So whenever you integrate by parts, that psi appears and psi vanishes on the boundary. Okay, and same thing is true here. Again there are no boundary terms, and you just get this term. And finally again you go back to the definition of psi and differentiate that with respect to yi, we have already done, and that is precisely yi by 2s. There is a 2 there, so you get yi by s, yi by s. So each term in the summation vanishes, and therefore we get d chi by dr equal to 0. Okay. So we'll continue from this point and conclude this, prove the mean value property. Thank you.